Now, let us start from random variable. Definitions. A random variable says x is a real-valued function in x into bracket x defined for each outcome in a sample space x. That is, x is the outcome of an experiment, while x is the total outcome of that experiment, where each of outcome can be found. Types of random variable. And we have two types of random variable. The first one says discrete random variable, and second one is continuous random variable. Definition of discrete random variable. A random variable is said to be discrete if it takes on finite number of integer value. Example of discrete random variable. A fair coin is tossed 3 times. Let S denote the number of S which appears. This is the practical way of obtaining our sample space, where T stands for tail and H stands for head. The sample space for the toss of 3 fair coins is TTT, THH, HTH, HHT, HTT, THT, TTH, and HHT, which we see in the practical aspect. The value that S can take is 0, 1, 2, 3. Notice that for this example, the X values are countable outcome because you can count the possible values that X can take on, and the outcomes are random. The X values 0, 1, 2, 3. X is a discrete random. The outcome is countable. Probability distribution function (PDF) for a discrete random variable. If S is a random variable that can assume values x1, x2, and so on to xn with associated probabilities p1, p2, and so on to pn, then the set of ordered pairs sk, pk, where k equal to 1, 2 to n is called the probability distribution function (PDF) for a discrete random variable. Characteristic of probability distribution function (PDF). The first one says each probability is between 0 and 1. Include sum of the probability is equal to 1. Example of discrete random variable. A men's soccer team plays soccer 0, 1, or 2 days a week. The probability that they play 0 days is 0.2. The probability that they play 1 day is 0.5. And the probability that they play 2 days is 0.3. Find the long-term average, mu, or expected value of the days per week the men's soccer team plays soccer. Solution. To do the problem, first let the random variable x equal to the number of days the men's soccer team plays soccer per week. S takes on the values 0, 1, 2. Since x is the day the men's soccer team plays per week, x takes value is 0, 1, 2. And probability of x, according to the question, and when they play is 0 day, you have 0.2 probability. When they play 1 day, you have 0.5 probability. And when they play 2 days, they have 0.3 probabilities. And now, mathematical expectation. Mathematical expectation is the weighted average of the possible value of x. Each value weights by its probability. It is defined by expected value of x equal to summation of x1, f of x1, plus x2, f of x2, plus ... plus xn, f of xn. The expectation f of x is divided by mu or mu. It is called expected value or mean of x. Properties of expectation of a discrete random variable. 1. Expected value into bracket t x close the bracket equal to t expected value of open the bracket x close the bracket equal to t mu. Expected value of open the bracket x plus t close the bracket equal to expected value of open the bracket t close the bracket plus t equal to mu plus t. Proof of these properties. Example 1. Find the mean, variance, standard deviation of the random variable while having the distribution below. The solution to this example is displayed. Expected values of functions of a random variables. Definition. If S is a discrete random variable taking value x1, x2 and so on, and B is a function, B into bracket S is a new random variable, its expected value is given as this. Example 1. Let S be the value of a roll of one die and let y equal to x squared. Find the expected value of y. Solution. Let's make a table of the outcome of one die. Since we know that a die has 6 sides, so x1 take the value of 1, 2, 3, 4, 5, 6, and our function given is y equal to x squared. So therefore we need to square each value of x, and the probability that each of these sides will occur is 1/6 each. Since the question said that we should find the expected value of y, therefore the expected value of y are equal to 15.17. Example 2. Let S be the sum of rolling two dice. Suppose the payoff function is given by y equal to x squared minus 6x plus 1. Question now says, Is this a good bet? Let's make a table of the outcome of rolling 2 dice. So the sum of table 1 is displayed in table 2. To obtain the value of y, we're going to put each value of x into the equation given, which is y equal to x squared minus 6x plus 1. And when we put the first value of x, which is 2, into the equation, we have -7. And we continue like this until we get to the last value of x, which is 12. And we have 70. The PDF, the probability density function of 2 now equal to 1 over 36, which can be seen in the table 2. That is to say, 2 appear 1 and 3 appear twice. That's the reason why we have 2 over 36. 4 appear thrice. That's the reason why we have 3 over 36. And 5 appear 4 times. That's the reason why we have 4 over 36. 6 appear 5 times. That's the reason why we have 5 over 36. 7 appear 6 times. That's the reason why we have 6 over 36. And 8 appear 5 times. That's the reason why we have 5 over 36. 9 appear 4 times. 4 over 36. 10 appear 3 times. 3 over 36. 11 appear 2 times. 2 over 36. And 12 appear 1 time. 1 over 36. So to calculate the expected value, we use the formula. Expected value of y to be 14.14. Now the question is this a good bet? To answer this question, since the expected payoff is positive, hence the bet is worth taking. This is to say, the bet is a good bet. Example 3. What is the expected value y equal to 3x plus 12? Solution. Expected value of y now equal to 3 expected value of x plus 12. Moment of a discrete random variable. Type of moment of a discrete random variable. Let S be a random variable. Then the first type of moment a discrete random variable is moment of a random variable x about the mean, mu subscript r. And second one is moment of a random variable x about the origin, mu subscript r raised to power comma. Definition 1. The rth moment of a discrete random variable x about the mean is defined as mu subscript r expected value into the bracket x minus mu raised to power r, which equal to summation I ranges from 1 to n into the bracket x minus mu raised to power r p of x, where r equal to is 0, 1, 2 to n. Definition 2. The rth moment of a discrete random variable x about the origin is defined as mu subscript r raised to power iv equal to expected value of s raised to power r. It is equal to summation I ranging from 1 to n s raised to power r subscript I p into bracket x subscript I, where r equal to 0, 1, 2 and so on like that. When r equal to 0, mu subscript 0 raised to power comma equal to expected value of x raised to power 0 equal to expected value of 1, which is equal to 1. Therefore, the rth moment of a discrete random variable x about the origin when r equal to 0 equal to 1. When r equal to 1, moment of a discrete random variable about the origin, expected value of x raised to power 1 equal to expected value of x, which is equal to mu. That the rth moment of a discrete random variable x about the origin when r equal to 1 is equal to rth moment of a discrete random variable x about the mean. Relationship between moment about the mean and moment about the origin. In calculating rth moment about the mean, mu subscript r, the following relationship have been found useful. We know that moment about the origin when r equal to 1 is equal to moment about the mean. So therefore, moment about the mean subscript 2 equal to, this is telling us that the second moment about the origin minus first moment about the origin give us second moment about the mean. Third moment about the mean can be obtained by finding the third moment about the origin minus 3 second moment about the origin multiplied by first moment about the origin plus 2 multiplied by first moment about the origin cube. Fourth moment about the mean is equal to fourth moment about the origin minus 4 multiplied by third moment about the origin multiplied by first moment about the origin plus 6 times second moment about the origin times first moment about the origin square minus 3 times first moment about the origin raised to power 4. Example 1. Find the first 3 moments about the origin of the random variable x with the probability distribution below and use your result to find the corresponding moments about the mean. We have x -4, 2, 6. Probability of x 1/4, 1/2 and 1/4. Solution. The first moment about the origin is from the above distribution. The first moment about the origin is equal to the level of x, which is equal to summation of x p in bracket x, which is equal to -4 times 1/4 plus 2 times 1/2 plus 6 times 1/4. And the first one gave us -1 plus 1 plus 3/2. So therefore, the first moment about the origin is 1.5. The second moment about the origin is exponential of x squared is now equal to summation of x raised to power 2 p of x now equal to -4 squared times 1/4 plus 2 squared times 1/2 plus 6 squared times 1/4, which give us 4 plus 2 plus 9. And therefore, second moment about the origin equal to 15. The third moment about the origin is which is equal to exponential of x raised to power 3 equal to summation of x raised to power 3 p of x, which equal to -4 raised to power 3 times 1/4 plus 2 raised to power 3 times 1/2 plus 6 raised to power 3 times 1/4, which is equal to -16 plus 4 plus 54. And this third moment about the origin equal to 42. Now, we are going to obtain moment about the mean using the output of moment about the origin. Since first moment about the origin equal to 1.5, second moment about the origin equal to 15, and third moment about the origin equal to 42. First moment about the mean is expected value of x minus mu. Now, first moment about the mean is now equal to 1.5 minus 1.5. So, first moment about the mean equal to 0. The second moment about the mean is based on the relationship between the moment about the origin and moment about the mean. We have second moment about the mean equal to second moment about the origin minus first moment about the origin square. This is now equal to 15 minus into bracket 1.5 raised to power 2, which gave us 12.75. The third moment about the mean is equal to third moment about the origin minus 3 times second moment about the origin times first moment about the origin plus 2 times first moment about the origin raised to power 3 equal to 42 minus 3 into the bracket 15 times 3/2 plus 2 into the bracket 3/2 raised to power 3. And the first one gave us 42 minus 135 divided by 2 plus 27 divided by 4. So therefore, the third moment about the mean gave us -18.75. Example 2. Given that s is a random variable with probability function p of s equal to s divided by 3, s equal to 0, 1, 2. Find the first 4 moments about the origin. Use your result to find the second and third moments about the mean. Solution. First moment about the origin is s1 equal to 0 times 0 divided by 3 plus s2 equal to 1 times 1/3 plus 2 times 2 divided by 3. You have a 0 plus 1/3 plus 4/3, and therefore The first moment about the origin equal to 5/3. The second moment about the origin is excess value of x raised to power 2 equal to, which is equal to 0 square times 0 divided by 3 plus 1 square times 1/3 plus 2 square times 2/3. The first one give us 0 plus 1/3 plus 8/3, and the second moment about the origin give us 3. Third moment about the origin is expected value of x raised to power 3. Expected value of x raised to power 3 equal to x1 raised to power 3 p of x1, x2 raised to power 3 p of x2 plus x3 raised to power 3 p of x3. It gives us 0 raised to power 3 times 0 divided by 3 plus 1 raised to power 3 times 1 divided by 3 plus 2 raised to power 3 times 2 divided by 3. It gives us 0 plus 1/3 plus 16/3, which is equal to 17 divided by 3. And the third moment about the origin gave us 5 whole number 2/3. Fourth moment about the origin is expected value of x raised to power 4, and it gives us x1 raised to power 4 p of x1, x2 raised to power 4 p of x2, and plus x3 raised to power 4 p of x3. Now we have 0 raised to power 4 times 0 divided by 3, 1 raised to power 4 times 1 divided by 3 plus 2 raised to power 4 times 2 divided by 3, which is equal to 0 plus 1 divided by 3 plus 32 divided by 3. That gives us 33 divided by 3. Fourth moment about the origin equal to 11. Therefore, the first moment about the origin equal to 5/3. Second moment about the origin equal to 3. Third moment about the origin equal to 5 whole number 2/3. And fourth moment about the origin equal to 11. The moment of random variable is about the mean. Since first moment about the origin equal to 5/3, and second moment equal to 3, third moment equal to 5 whole number 2/3, and fourth moment equal to 11. The second moment about the mean is mu2, which is equal to mu sub square 2 equal to second moment about the origin minus first moment about the origin square. It gives us 3 minus into the bracket 5/3 square, which is equal to 3 minus 25 divided by 3. And second moment about the mean equal to 2/9. The third moment about the mean is, I will have 5/2, 5 whole number 2/3 minus 3 into the bracket 3 times 5/3 plus 2 into bracket 5/3 cube, which is 17 divided by 3 minus 45 divided by 3 plus 250 divided by 27. The third moment about the mean equal to -2 divided by 27. How to use moment generating function to prove some distribution. I would like to start from binomial distribution. The PMF of binomial distribution is f into bracket s equal to n combination s, p raised to power x, q raised to power n minus x. Our moment generation function formula is m into bracket theta equal to express value into the bracket exponential raised to power theta x. And the third equation gives us the summation s ranges from 0 to n of moment generation function times PMF of binomial. In this bracket, we can see that p exponential raised to power theta into bracket r raised to power x, because p and exponential raised to power theta x in equation 3 has s in common. That's the reason why we have this. And the last equation here, which is m into bracket theta equal to into bracket p exponential raised to power theta plus q into bracket r raised to power n, is binomial expansion. To find the mean and variance of binomial distribution using moment generating method, we are going to differentiate the last equation once. And when we differentiate the last equation there, that is our moment generating function, we have m raised to power 1, that is to say, that one means that we differentiate the moment generation function once, which gives us np exponential raised power theta into bracket p exponential raised power theta plus q all into bracket n minus 1 because we differentiate it once. And therefore, we now say that let theta equal to is 0. And when our theta is equal to is 0, the equation 2 gives us that np exponential raised power is 0 into the bracket p exponential raised power 0 plus q into bracket n minus 1. In equation 3, we know that exponential raised power 0 will be 1 by pressing our calculator. So therefore, in equation 3, we have np into bracket p plus q close bracket raised by n minus 1. Based on binomial rule, we know that p plus q equal to 1. Our expected value using moment generation method of binomial equal to np. To obtain the variance of binomial distribution using moment generating function method, we have this. That is, our variance of s equal to differential of moment generation function twice into the bracket 0 minus into the bracket moment generation function when we differentiate moment generation function once all raised to power 2. And when we differentiate moment generation function twice, these are the process used. This is the result of when we differentiate moment generation function once. Now say by using product rule, we say let u equal to np exponential raised power theta and v equal to into the bracket p exponential raised power theta plus q close bracket all raised power n minus 1. Now say that the u over the theta equal to np exponential raised power theta. That is, we differentiate u and we differentiate our v also, and the result gave us into bracket n minus 1 close the bracket p exponential raised power theta open the bracket p exponential raised power theta plus q close bracket all raised power n minus 2. So this is the result of when we differentiate moment generation function of binomial twice. And after that, say that let theta equal to 0. So therefore, in equation 2, any place we see theta, we represent it by 0. And any place we see exponential raised by 0, all will be equal to 1 by pressing our calculator. Equation 4 gives us np into bracket n minus 1, close bracket p, open bracket p plus q, close bracket raised by n minus 2 plus np, open the bracket p plus q, close the bracket raised by n minus 1. And we know that p plus q equal to 1 based on binomial rule. So we now have in equation 6 np into bracket n minus 1 close the bracket p plus np. So therefore, when we differentiate moment generation function twice and we make our theta to be 0, we have this n into bracket n minus 1 close the bracket p square plus np. So now we can find our variance of binomial distribution using moment generating function. We know that when we differentiate moment generation function twice, this is the result we obtain. And when we differentiate it once, this is the result we obtain. So therefore, by calculation, when we multiply this first one by n and p square, we have n square p square minus n p square plus this n p minus, when we use this square to open this bracket, we have n square p square. So by calculation, this one cancel this one, we have np minus np square. And when we factorize np out, we have np into bracket 1 minus p, and we know that 1 minus p equal to q based on binomial rule. So therefore, our variance of binomial distribution using moment generating function method is npq. The next distribution is Poisson distribution, and the PMF of Poisson is f of x into bracket lambda raised power x exponential minus lambda divided by s factorial. And this is the moment generating function formula. So by putting our PMF of Poisson into the equation, we have summation x ranging from 0 to infinity exponential theta x lambda raised to power x exponential raised to power negative lambda divided by s factorial. And when we factorize x out of exponential raised to power theta x and lambda raised to power x, we have into the bracket x into the bracket exponential raised to power theta lambda close the bracket raised to power x exponential raised to power negative lambda, everything divided by x factorial. So therefore we factorize exponential raised to power negative lambda out, and we have summation s ranges from 0 to infinity into the bracket exponential raised to power theta lambda close the bracket all raised to power x divided by s factorial. And by using power series expansion for exponential function, from there we see that summation s ranging from 0 to infinity into the bracket exponential raised to power theta lambda close the bracket all raised to power s divided by s factorial equal to exponential raised to power lambda theta. So therefore we represent everything here by exponential raised to power lambda theta, and this is the equation we obtain. And from this place we factorize, and from this place we know that exponential common to both of them, so therefore we write one exponential, and this negative lambda, this is it, and this one we have 1 minus exponential raised to power theta based on exponential sum. For our moment generation function for Poisson is now equal to m into bracket theta equal to exponential raised to power negative lambda into bracket 1 minus exponential raised to power theta. So to obtain our expected value of Poisson distribution using moment generating function method, we need to differentiate our moment generating function we obtained before, which is exponential raised to power negative lambda into the bracket 1 minus exponential raised to power theta close the bracket. And to make it easy, we open the bracket and we have exponential raised to power negative lambda plus lambda exponential raised to power theta. So therefore we differentiate this one and we obtain lambda exponential raised to power theta exponential raised to power negative lambda into the bracket 1 minus exponential raised to power theta back. So we now equate theta to be 0, that is when theta equal to 0. So therefore any place we see theta in equation 3, we are representing it with 0, and we have, and in equation 4 we have lambda exponential raised to power 0 exponential raised to power negative lambda into bracket 1 minus exponential raised to power 0, and this one gives us lambda times 1 times 1, as we know that exponential raised to power theta equal to 1. So therefore our expected value of Poisson distribution using moment generating function method is lambda. To obtain the variance of Poisson distribution using moment generating function method, we need to differentiate the moment generating function we got before in second time. And by using product rule, we have u times dv d theta plus v times du d theta. And we say that let our u equal to lambda exponential raised to power theta and v equal to exponential raised to power negative lambda into bracket 1 minus exponential raised to power theta. By differentiate u, we have exponential raised to power theta lambda. And by differentiate v, we have lambda exponential raised to power theta exponential raised power negative lambda into bracket 1 minus exponential raised power theta. Based on this equation, we have u dv d theta plus v du d theta. That is how we get this equation 1. By when our theta equal to 0, any place we see theta in equation 1, we replace it with 0 in equation 2. Therefore, our equation 3, we have lambda into bracket lambda plus lambda. So therefore, the variance of Poisson distribution using moment derivation function is also lambda. The third distribution is exponential distribution, and the PDF of exponential distribution is f of x equal to lambda times exponential raised power lambda x, where x greater than or equal to 0. 0 otherwise. And this is the moment generation function formula. So therefore, in this place, because exponential distribution is a continuous distribution, so therefore we have integral of 0 into infinity exponential raised to power theta x into the bracket the PDF of exponential distribution. So we factorize lambda out, and we have integration of 0 into infinity exponential raised to power theta x into bracket exponential raised to power negative lambda x close the bracket dx. So therefore we factorize exponential out, and we have lambda integration of 0 to infinity exponential raised to power into the bracket x theta plus into bracket negative lambda x close the bracket dx. So in the last equation, we represent into the bracket lambda minus theta x by b, and we differentiate that b with respect to the x, and we have lambda minus theta. So we want to make the s subject of formula, and that's the reason why we have equation 3 here. So we just divide both sides by lambda minus theta, and therefore our dx equal to db divided by lambda minus theta. So therefore, any place we see lambda minus theta into the bracket x, we represent it with b by b, and any place we see the s, we are going to write db divided by lambda minus theta, and that is what we have here. So we factorize lambda minus theta out, and we have lambda divided by lambda minus theta exponential integration of 0 to infinity exponential raised by minus b db there. And we can see that our integral from 0 to infinity exponential raised by b db vanished, because when we prove it further, we are going to obtain 1. So in the equation, that's the reason why we have lambda divided by lambda minus theta in equation 3. And that of equation 4, we just use lambda to divide everything. So therefore, our moment generation function equal to into the bracket 1 minus lambda divided by theta close the bracket raised to power negative 1. So therefore, when we differentiate the moment generation function of exponential distribution, once we have this one, and when we equate the theta into the 0, we have this. So therefore, the expected value of exponential distribution using moment generating function method is 1 over lambda. So we want to obtain our variance of exponential distribution using moment generating function based on the previous explanation by using product rules. We have this one when we differentiate a moment generation function of exponential distribution twice, and when we equate theta to 0, we have this one. So therefore, when we differentiate moment generation function of exponential distribution twice, and we equate theta to 0, we have 2 divided by lambda square. So variance of exponential distribution using moment generating function method is now equal to 1 divided by lambda square. Proving of some discrete random variable. I would like to start from binomial. Binomial distribution. This distribution deals with repeated and independent trials of an experiment with two outcomes resulting in either 0 or 1, yes or no, success or failure, true or false. If the interest is on the number of sources and not in the order in which they occur, the probability of exactly x successes in n repeated trials is given by the probability function of a binomial random variable x. This is the probability of having x success in a series of n independent trials when the probability of success in any of the trials is p. That is, our x is the number of success in n independent trials, while p is the probability of success. Proving. If S is a random variable with this probability distribution, then the expected value of X is given as expected value of X equal to summation of X ranges from 0 to n, X probability distribution function of binomial distribution, which is this, where n combination X is defined as this. And don't forget, our Q equal to 1 minus P anytime we have Q. The second equation shows the expansion of combination, which is n factorial divided by x factorial into the bracket n minus x factorial multiplied by p raised to power x into the bracket 1 minus p raised to power n minus. The third equation, we need to expand the factorial in the equation. Now we want to expand it. In the fourth equation, which is this equation, we factorize np and s divided by x out of the equation. So we now use the math to open this bracket in the third equation. We have this one. So after that, now say that let y equal to x minus 1 and m equal to n minus 1, then n minus 1 equal to x minus 1. We have m here because we said that let m equal to n minus 1. And here we have y because we said that let y equal to x minus 1. The brackets here, we have m minus y. If you look at this place and we look at what we have here, we will see that they are the same thing. So therefore, we represent m minus y with all these things. Let p equal to a and b equal to 1 minus p. The binomial theorem says that bracket of a plus b raised to power m equal to everything a. So therefore, we can turn everything in this place into a plus b raised to power n based on binomial theorem. And we say that a is our p, this plus is this, b is 1 minus p. And if you look at what is a, we can say that p cancel p, remain 1, and 1 raised to power anything is 1. So therefore, everything that is a is 1. Therefore, our expected value of binomial distribution is now NP. To prove the variance of binomial distribution, variance of x equal to expected value of x squared minus into the bracket expected value of x raised to power 2. That is to say, expected value of x squared can be expounded as. So therefore, we need to consider the x squared, which is expected value of x into bracket x minus 1, now give us this thing. And based on our proving before, we have x into bracket x minus 1 and n combination x give us this one. Put our p raised by x into bracket 1 minus p raised to power n minus x. So everything here is this one. We factorize p squared and n into bracket n minus 1 out with that of x into bracket x minus 1. Let y equal to x minus 2 and m equal to n minus 2. Our x squared is now n into bracket n minus 1. Close the bracket, p raised to power 2. To calculate the variance, so we just put what we have before into this. By opening all the brackets, we have this one. We just factorize np out. So therefore, the variance of x of binomial distribution gives us np into bracket 1 minus p. Example of binomial distribution. Example 1. A factory produces tools of which 98% are in good working order. Samples of 1,000 tools are selected at random and tested. Question A. Find the expected value that the tool is in good working order and give it a practical interpretation. Question B. Find the standard deviation of the number of tools in good working order in this example. Solution. The probability that the tool selected is in good working order is P equal to 98% according to the question, which we have 98 divided by 100, which gives us 0.98. The probability that the tool selected is not in good working order is 1 minus probability that the selected tool is in good working order. Probability that the tool selected is not in good working order is 0.02. N equal to the number of trials in a binomial experiment, which is 1000. Solution to question A. The expected value according to the proofing is expected value of x equal to np, where n equal to 1000 and p equal to 0.98. So therefore, the expected value is 980. Interpretation. This simply means that in a sample of 1000 tools, 98 tools are expected to be in good working order. Standard deviation. From the proving above, variance x equal to np into bracket 1 minus p. So standard deviation equal to square root of variance, which is square root of np into the bracket 1 minus p. And our n equal to 1000, p equal to 0.98, and 1 minus p equal to 0.02. So therefore, the standard deviation is 4.4272. Example 2 of binomial distribution. Find the probability that at least 5 heads show up when a fair coin is tossed 7 times. Solution. The probability that a head will show up when a fair coin is tossed is p equal to 0.5, because a fair coin has just ordinary 2 sides, and the probability that one of these sides will show up is 1/2, which is 0.5. Therefore, the probability that will not show up is 1 minus 0.5. So p equal to 0.5, 1 minus p equal to 0.5, n equal to 7, the number of trials. Let s be the number of L's that show up. Obtaining at least 5 L's is equivalent to showing x equal to 5, 6, 7. If they say that at least, that is to say it can be more than, they started from that mentioned number, which is 5, 6, 7 till the last number. The probability that at least s equal to 5 equal to probability equal to 5 or 6 or 7 using this formula of binomial. So we have 7 combination 5 in the bracket 0.5 raised to power 5 into bracket 1 minus 0.5 raised to power 7 minus 5 plus combination of 7 combination 6 multiplied by into bracket 0.5 raised to power 6 multiplied by into bracket 1 minus 0.5 raised to power 7 minus 6 plus 7 combination 7 multiplied by 0.5 into bracket 0.5 raised to power 7 multiplied by into bracket 1 minus 0.5 raised to power 7 minus 7. And this combination is expanded here. And the answer for the first one is 0.17, 1641 plus second one 0.0547, third one plus 0.0078, and the probability that at least 5 will show up is 0.2266. Now, Poisson distribution. I want to show how to prove the mean and variance of Poisson distribution. Probability distribution function of Poisson is this. Following the same step in that of binomial, just follow the same step you have, and this one we see, just put the value of PDF, probability distribution function, into it, expand it, and this one is this one, you have it here, expand what they call it the factorial side. Now say that let t equal to x minus 1. Put t in every place we have x minus 1 and factorize lambda out. And this place alone is saying that using the power series expansion of the exponential function, this place alone giving us this. So expected value of Poisson distribution is pi. Proving the experience of Poisson distribution. Follow the same trend we follow in binomial. Just follow the same trend. We have the same thing here. And the variance is lambda. That is to say, variance, mean and variance are the same. Example of Poisson distribution. Ade receive an average of 2 tests every 3 minutes. If we assume that the number of tests is Poisson distribution, what is the probability that he receives 5 or more tests in a 9-minute period? Solution. Let S be the number of tests in a 9-minute period. Then 2 tests every 3 minutes is the average, it's lambda. So therefore, lambda equal to 3 multiplied by 2. Our lambda equal to 6. Probability that A receive 5 or more tests in a 9-minute period is now equal to S greater than or equal to 5, which is leading us to 1 minus probability that X less than or equal to 4. And this is our probability distribution function of Poisson. So we calculate for is 0, that is we are going to start from is 0, 1, 2, 3 and 4. When we calculate everything, we have 0.2851, and we say that probability that it is more than 5 or more is 1 minus probability that it is less than or equal to 4. You can say that 1 minus probability that it's less than or equal to 4, and the probability that receive 5 or more is 0.7149. Proof. Discrete uniform distribution and negative binomial distribution. Discrete uniform distribution. The probability distribution function of discrete uniform distribution is given as this. Expected value of discrete uniform distribution. Expected value of x equal to summation of x ranging from 1 to n x probability distribution function of discrete uniform distribution, which is this. Equation 2, we put the probability function of discrete uniform distribution into the equation, which is 1 over n. In this equation, we factorize 1 over n out of the equation, and we have summation of x ranges from 1 to n x. So we expand the summation of x ranges from 1 to n as 1 plus 2 plus 3 plus ... plus n. And this 1 plus 2 plus 3 plus dot 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 plus n can be expanded as this. And if we look at the expansion of 1 plus 2 plus 3 plus dot 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 plus n, we see that we say, let's write 1 plus 2 plus 3 plus dot 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 plus into the bracket n minus 2 plus into the bracket n minus 1 plus n. Write the reverse order of the equation above. That is, write the reverse, that is, write 1 plus 2 plus 3 plus dot 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 plus n plus into the bracket n minus 2 close bracket plus into the bracket n minus 1 close bracket plus n. Write the reverse of it, which is n plus into the bracket n minus 1 plus into the bracket n minus 2 plus dot 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 plus 3 plus 2 plus 1. Add both equations together, that is equation, the first one and the second one. When we add these two together, we have into bracket n plus 1 plus into bracket n plus 1 plus into bracket n plus 1, and so on like that. And that's the reason why when we see that all is n plus 1, now write n into bracket n plus 1. That is to say, n outside represents the nth time of n plus 1 and into the bracket n plus 1. And if we look at this equation very well, that is, we had two equations together to get n to bracket n plus 1. That's the reason why we divide it by 2. And that is where we get this equation 1 into the bracket 1 over n multiplied by into the bracket n plus 1 divided by 2. When we multiply it together, we have n is bracket n plus 1 all over 2n, and n cancel n, so therefore our expected value equal to n plus 1 all over 2. That's the expected value of discrete uniform distribution. Variance of discrete uniform distribution. We have variance of x equal to the expected value of into the bracket x squared minus into the bracket the expected value of x all raised to power 2. So consider expected value x raised to power 2. We have which is equal to summation of x is from 1 to n x squared 1 over n, which is the PDF of discrete uniform distribution. We factorize 1 over n out, and we have summation of x ranging from 1 to n x squared. We have into the bracket 1 over n multiplied by, we expand the summation of x squared, which gives us the bracket x squared plus 1 squared plus 2 squared plus 3 squared plus dot plus n squared. We have to expand the into bracket 1 squared plus 2 squared plus 3 squared plus dot plus n squared. We obtain n into bracket n plus 1. Open another bracket 2n plus 1. Everything divided by 6. That's what we are going to obtain. So in the next equation we have, by multiplying 1 over n with the expansion of this, we have n into bracket n plus 1 to bracket 2n plus 1 divided by 6n, and n cancel n. We have expected value of x squared to be equal to n plus 1 in the bracket 2n plus 1, everything divided by 6. So variance, now variance of x equal to Substitute the value of x, expected value of x squared minus expected value of x raised by 2 to the equation of variance. We have n into the bracket n plus 1, close bracket, open another bracket, 2n plus 1, everything divided by 6 minus, open the bracket, n plus 1 divided by 2 all square. And when we expand that of n plus 1 divided by 2 all square, we have the equation 2, which is n plus 1, close the bracket, open another bracket, 2n plus 1 divided by 6 minus n plus 1, close the bracket, open bracket, n plus 1 divided by 2 square. By opening the bracket up, we have 2n square plus n plus 2n plus 1 divided by 6 for the first one. For the second one, minus n squared plus 2n plus 1 divided by 4. We now find the LCM of both 6 and 4, which is 12. Say 6 in 12, we have 2. Now use 2 to multiply 2n squared plus 3n plus 1. We have 4n squared plus 6n plus 2. And 4 in 12, we have 3. Now use that 3 to multiply n squared plus 2n plus 1. And all the negative we have there is this negative. So we have negative 3n squared plus 6n minus 3. So 4n squared minus 3n squared, we have n squared plus 6n minus 6n cancel each other, plus 2 minus 3 equals minus 1. So we have n squared minus 1 divided by 12. Our variance of x of discrete uniform distribution equal to n squared minus 1 divided by 12. A sample of discrete uniform distribution. What is the expected value, variance, standard deviation of discrete uniform distribution of rolling one die? Solution. Let random variable s represent the outcome of the die. Therefore, our s equal to 1, 2, 3, 4, 5, 6, because the die has 6 sides and our n equal to 6. So expected value of x now equal to n plus 1 divided by 2 according to the proving. Now equal to where our n is equal to 6. So therefore we now have 6 plus 1 divided by 2. 6 plus 1 equal to 7 divided by 2. So therefore our expected value equal to 3.5. The average of the outcomes should be midway between 3 and 4. Variance of x now equal to n squared minus 1 divided by 12. And our n equal to 6. So therefore we now have 6 squared minus 1 divided by 12. And 6 squared equal to 36 minus 1 divided by 12. We now have 35 divided by 12. Variance of s now give us 2.9167. So standard deviation is the square root of variance of x, and our variance of s of discrete uniform distribution is 2.9167. 2.9167, and square root of 2.9167 equal to 1.7078, which is our standard deviation. Negative binomial. Negative binomial distribution. Negative binomial distribution has two forms of probability distribution function, and they are: first one is called to P of P into bracket S equal to X slash R, P equal to combination X plus R minus 1 combination X multiplied by P raised by R into the bracket 1 minus P raised by S, where S ranges from 0 to infinity. and p is 0 less than or equal to p less than or equal to 1, 0 otherwise. And the second one is p the bracket variable y equal to y plus r comma p equal to y minus 1 combination r minus 1 p raised by r the bracket 1 minus p raised by y minus r, where x equal to r comma r plus 1 comma dot 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 0 otherwise. But the second distribution can be obtained from the first one by putting y equal to x plus r. Proving of expected value of negative binomial. We have summation s ranges from 0 to infinity x probability distribution function of negative binomial, which is equal to summation of x ranges from 0 to infinity x combination p r is bracket 1 minus p raised by x, which is probability distribution of negative binomial. When we look at that of summation x ranges from 0, if we put a 0 in our equation 2, everything will be in 0. So therefore, we need to start from 1. That's the reason why we have s ranging from 1 to infinity in that third equation. So expanding the combination for in equation 3, we have equation 4, which is s ranging from 1 to infinity x into the bracket s plus r minus 1 close the bracket factorial divided by x factorial into the bracket r plus x minus 1 minus x close bracket factorial multiplied by r raised by r p raised by r into the bracket 1 minus p raised by s. Note, in expanding the x factorial, this is this, and each of these one are this. In equation 4, we see that in the numerator plus x cancel negative x. That's the reason why we have equation 5. Ask summation s ranges from 1 to infinity x into the bracket r plus x minus 1 close the bracket factorial divided by s factorial into the bracket r minus 1 close bracket factorial p raised to power r into the bracket 1 minus p raised to power x. And if we look at this place, we say that r minus 1 close bracket factorial equal to r factorial divided by r. So therefore we substitute that into the equation 6, and we substitute x factorial to be equal to x into bracket x minus 1 bracket factorial into equation 6 also. And equation 7, we just rewrite the r factorial divided by r. In equation 8, we factorize r and s divided by x out of the equation. So s cancel x, we have the next equation, which is this equation. And if we look at what we have there in the second to the last equation, we can write it in combination form as this. Now we want to make the last equation, this equation, to be like the first probability distribution function of negative binomial. Now say that let y equal to x minus 1, which infers that x equal to y plus 1, and b equal to r plus 1, which means that r equal to b minus 1. Now say that r plus x minus 1 equal to b minus 1 plus y plus 1 minus 1. So r plus x minus 1 there now equal to b plus y minus 1. And since we know that y equal to x minus 1 and x equal to 1, we now say that y equal to 1 of the value of x minus 1 there. So y equal to 0. So by substituting b and y into the equation, we have this equation. And this equation, we can see that we split out the p raised to power b minus 1 to 2. That is to say, we now have p raised to power b and p raised to power negative 1. Also, we have in the bracket 1 minus p raised to power y, the bracket 1 minus p raised to power 1. We factorize r p raised to power negative 1 in the bracket 1 minus p raised to power 1 out of the equation. And the remaining equation is a probability density function of negative binomial. And anytime we have summation of probability density function of any distribution, that will be 1. So that is where we get that one. And we now say that our expected value of negative binomial by proving now equal to r into bracket 1 minus p divided by p. Variance of negative binomial. And we know that our variance of x equal to expected value of x squared minus the bracket s into bracket expected value of x everything square. And we know that we can expand our expected value of x squared as expected value of x into bracket s minus 1 plus expected value of x. So therefore our variance now equal to expected value of x into bracket s minus 1 plus expected value of x minus into bracket expected value of x everything square, by considering expected value of x the bracket x minus 1, which will be this equation. It will be this equation. And if we look at the ranges of x, we switch from s ranges from 0 to infinity to s ranges from 2 to infinity, because if f is 1, all the equation will be vanished. That's the reason why we switch. That's the reason why we start from s ranges from 2 to infinity. And when we're talking about x into bracket x minus 1 combination r plus x minus 1 combination x, we can write it as equal to x in the bracket x minus 1 to the bracket r plus x minus 1 factorial divided by r minus 1 factorial s factorial. And by expand this equation, we have this. So that's how we get all this place. So after that, now say let's y equal to x minus 2, which implies that x equal to y minus 2, and b equal to r plus 2, which implies that r equal to b minus 2. So therefore r plus x minus 1 equal to b minus 2 plus y plus 2 minus 1. Therefore our r plus x minus 1 equal to b plus y minus 1. So we now substitute y, b, and r plus x minus 1 in this equation. So and we have r into bracket r plus 1 summation y ranges from 0 to infinity, b plus y minus 1 combination y, b raised to power b minus 2 in the bracket 1 minus b raised to power y minus 2. So by expanding this equation, we have this equation, and we know that summation y ranges from 0 to infinity, b plus y minus 1 combination y, b raised to power b into bracket 1 minus p raised to the power y. Probability distribution function of negative binomial. So therefore this one now equal to 1. Now have r into bracket r plus 1 into bracket 1 minus b raised to the power 2 divided by p square times 1. Our expected value of x into bracket x minus 1 equal to r into bracket r plus 1 close bracket open another bracket 1 minus p close bracket square divided by p square. So therefore our variance by substituting for expected value of x into bracket x minus 1 plus expected value of x minus expected value of x all square. By substituting, well, then we have this equation. Now factorize r into bracket 1 minus p divided by p out of the equation because it's common to all of the term. So we have r into bracket 1 minus p divided by open bracket r plus 1 close bracket 1 minus p close the bracket divided by p plus 1 minus r into bracket 1 minus p divided by p. So by open all the brackets up, we have this equation. And by the calculation, we have into the bracket 1 over p. By multiplying this together, we see that our variance negative binomial distribution now equal to r into bracket 1 minus p divided by p square. Thank you for watching. Please don't forget to subscribe to my channel. Thank you so much. I really appreciate it.